On to section 5.9, factorization of non-negative definite matrices. The real topic is Cholesky factorization. We've already looked at the square root of a symmetric non-negative definite matrix back in section 3.8, I think it was. And we'll start out by establishing that that square root is unique, and then we'll move on to this new type of factorization. Okay, recall Theorem 3.8.15. For a symmetric positive definite matrix A, there's an orthogonal matrix V and a non-negative definite matrix S, such that VS V transpose squared equals matrix A. 3.8.15, let's run back and look at that. It's part 2 is given here. And we stated symmetric matrix, non-negative definite. Then there's a matrix VS V transpose such that when it's squared, it gives matrix A. By the way, we had created S using, we actually used the square roots of the eigenvalues of matrix A is where those came from. We saw in the proof. When we went through establishing that. But this simply established the existence of such a matrix such that when we square it, then we get something we call the square root. It didn't deal with the uniqueness, and that's what we're about to deal with. So matrix has a square root. We denoted this VSV transpose as the square root of A to the 1/2. And now we're going to show that such a matrix is unique. So let A be a symmetric non-negative definite matrix, and let B be a symmetric non-negative definite matrix such that B squared equals A. Claim is V equals C to the 1/2. B equals V, C to the 1/2, V transpose. That is VS, V transpose, where S is C to the 1/2. It must be equal to this. The diagonal matrix with entry square roots of the C's, where the C's are the eigenvalues of A. And matrix V is orthogonal. Okay, let's go to the proof of that. 5.9.1. Okay. All right. Quotes and theorems, we'll kind of bounce back and forth and look them up. Theorem 3.8.A and Theorem 3.8.10 said matrix A, symmetric matrix, non-negative definite, can be written as A equals VC V transpose, where V is orthogonal. Let's look up Theorem 3.8.A. Okay, back to the notes. And I think I've got that waiting right here. Yeah, if A is a real n by n matrix, it's orthogonally diagonalizable if and only if it's symmetric. We have symmetry, so we've got the orthogonal diagonalizability. Whoops, in what we're doing. Back to the proof. Okay, we were given symmetric, and that'll give us the orthogonal diagonalizability. Theorem 3.8.10 just guaranteed that the C matrix, the diagonal matrix, would have to have the eigenvalues of A as its diagonal entries. It also guaranteed, we're not going to use it in this particular proof, but it also guaranteed that matrix V was of a particular form as well. But matrix C, that part we need. And we're going to consider, for reasons to be made apparent later, B minus V C to the 1/2 V transpose squared. Okay, we're actually trying to show B equals V C to the 1/2 V transpose. So that's the goal in the computations. For now, consider B minus V C to the 1/2 V transpose squared. Take that quantity, multiply it by itself. Do your FOIL thing, so distribute basically, will produce a product of this form. Now, let's take this expression and write it as a transpose. So we're going to transpose this, write each of the entries down backwards with a transpose on the outside, having transposed each of those. Remember, C is a diagonal matrix, so it's its own transpose. So I don't need to transpose on the C to the 1/2 matrix. And let's see, B transpose equals B. Hypotheses, B was symmetric. So we can replace this B transpose with a B, and we can express this quantity squared in terms of this. We also made a substitution, B squared equals A, along the way. We had an A at this end, we had an A at that end. This quantity squared is matrix matrix A as well. So anyhow, it simplifies down to this amount here. All right. We'll be back to look at this quantity. Let's name it equation star asterisk. And we need to do some more computations. Okay, since B itself is symmetric and non-negative definite, part of the hypotheses, then by theorem 3.8.15 part 2, we recently looked at that one, or did we? No, this deals with the orthogonal diagonalization. Let's go find that one. 3.8.15. Let's see, was that? Yeah, we did look at that one recently. Non-negative definite matrix, symmetric, has this type of orthogonal diagonalization. So we're applying this result now to matrix B. So matrix B is of the form some orthogonal matrix, let's call it U, D, U transpose, for some diagonal matrix D. Each of the D sub i's are non-negative, theorem 3.8.14, I've got it hiding in the background somewhere. That said, if you've got a non-negative definite matrix, then the eigenvalues are non-negative. If you've got a positive definite matrix, the eigenvalues are positive, it also claimed. But that gives us that these diagonal entries, D1 through D sub n, these must be non-negative. These are the eigenvalues of matrix B, in fact. Okay, let's look at V transpose U D squared. Okay, that'd be V transpose U D. Let's insert a U transpose U, where U was introduced above. U's orthogonal, so that's just an identity. Here's the other D to give you the D squared, and another U transpose U. Identity matrix, U is orthogonal. U inverse equals U transpose. Property of orthogonal matrices that we've used repeatedly. Let's associate things a little differently. Here, so move the parentheses around. Here we've got a UDU transpose. Here's another UDU transpose. Why, that's what we had as matrix B. That's where the U's and the D's came from. So we've got a B here and a B here. This equals V transpose, B squared, U. Well, B squared equals A, hypotheses in the theorem. So we'll make that substitution. We also had, first line of the proof, we had A written as V, C to the 1/2, V transpose. So we're substituting that for A. Sorry, we had this squared equals A. So we're substituting that for A, V, C to the 1/2, V transpose squared. And let's see, we'll write that out. So you could use some parentheses here. So we've written that down twice. So we've got V transpose, VC to the 1/2 V transpose, VC to the 1/2 V transpose, VC to the 1/2 V transpose. So we got two copies of that times U. Here's a V transpose V. Here's another one. You like those. V's orthogonal. So those are identity matrices. So we lose the V transpose V's in both cases. We keep a C to the 1/2, another C to the 1/2, V transpose U, right? C's diagonal, the C to the 1/2 thing times itself gives the matrix C. We had the square roots in the C to the 1/2, so this is the computation we get here. Now we've shown, for some reason, that V transpose U D squared equals C V transpose U. an important equation. Let's call it double asterisk. We're trying to get back to that squared matrix involving B and some other things, but it takes a while. Okay, let the ij entry of V transpose U, notice V transpose U occurs on both sides of these equations, on the left here and on the right here, but let Z sub ij be the entries of V transpose U. D is diagonal. The ij entry then of V transpose U times D squared is also diagonal, would be the Z sub ij's times the diagonal entries of this matrix D squared. So that's what we get for the ij entry of this product, follows from the definition of ij entry and the fact that D squared is a diagonal matrix. So when I run along column of this matrix, we only pick up the entry on the diagonal that matters. We pick up a bunch of zeros, but they're gone in the summation for the definition of matrix product. Similarly, C is diagonal. So here we've got in this product C times V transpose U. We've got a diagonal matrix times this V transpose U, the entries of which we have said are the Z sub ij's. So the ij entry from the definition of matrix product of this matrix will be C sub I, Z sub ij. Now, we just showed those two matrices are equal. So the ij entry of the one on the left, Z sub ij, D sub j squared, must equal the ij entry of the one on the right, Z sub I, Z sub ij, as given here. Let's rearrange a wee bit and multiply both sides by Z sub ij to yield D sub j squared, Z sub ij squared, C sub I, Z sub ij squared. So we rearranged on the left, multiplied both sides by Z sub ij, picking up a second power on these because we want to take square roots. Let's take a square root of both sides. Then the D sub j's, they were eigenvalues of matrix B. It was positive, non-negative definite. So anyhow, these are non-negative. The eigenvalues are non-negative. You observe that above. So when you take the square root of D sub j squared, okay, you get the absolute value of D sub j, but these are non-negative. So we can drop the absolute value there. We take the square root of the Z sub ij squared. We are stuck with absolute values on both of those. And you take the square root of the C sub I and you get, well, the square root of C sub I. They were eigenvalues of a non-negative definite matrix as well, and so are positive. So square roots make sense there as well. All right. So I want to get rid of the absolute values. Let's multiply both sides by the sign of Z sub ij. +1 if Z sub ij is positive, -1 if Z sub ij is negative, and 0 if Z sub ij is 0. So multiply both sides by that same quantity. Hey, the sign of a number, the SIGN sign of a number, and the absolute value of the number together yield the number. So we'll produce a Z sub ij from both of these. That was the purpose of doing that. So we get this relationship. D sub j, Z sub ij equals C sub I to the 1/2 Z sub ij. All right. The ij entry of V transpose UD is Z sub ij, D sub I, similar to what we had up here, except up here we were looking at D squared. The ij entry of C to the 1/2 V transpose U is similar to what we had up here, so we get a square root on that. So we get a C sub I to the 1/2 Z sub ij. We just showed these quantities are equal, didn't we? Little error here. This should be a D sub j. We should have Z sub ij, D sub j. Sorry, always typos. That's the same thing we had up top, right? Z sub ij, D sub j squared. Well, we considered the matrix D squared there. So yes, sorry, should read D sub j on this side. Then we've shown those two quantities are equal. So the ij entry of this matrix is the same as the ij entry of this matrix. In other words, this matrix, V transpose UD, equals this matrix, C to the 1/2 V transpose U. For what it's worth, I mean, it's a computational proof. So what inspires them to look at this, well, won't really fall into place until near the end. But we've shown V transpose UD equals C to the 1/2 V transpose U. Remember that, we'll recall it when we need it. Okay, so if we look at V, C to the 1/2 V transpose B, we can replace the B with UD U transpose. That's where the UD U transpose stuff came from, so make that substitution. Let's see, do some association, associate these three, otherwise we've kept everything the same. V transpose UD, well, we were just talking about that. V transpose UD, we just established on the previous slide, is C to the 1/2 V transpose U. Okay, so make that substitution. That gives us a C to the 1/2 and a C to the 1/2. So we'll combine those to get matrix C. And I guess that's about it. Oop, not quite. We've got a UU transpose over here on the right. U is an orthogonal matrix, gives an identity, and that we can drop, and we get VC V transpose. And we started this first line of the proof, A equals VC V transpose we had originally. Okay, so we've shown, let's see, that this quantity equals A. Remember equation star from, was it the first slide or the second slide? We had taken B minus VC to the 1/2 V transpose squared, and we had rewritten it like this. So there's the computation from above. Now we're ready to start substituting some stuff in and simplify. Okay, we have, let's see, VC to the 1/2 V transpose B. Actually got that in two places. We just showed that quantity equals matrix A. So we can replace this with matrix A, and we can replace the stuff in parentheses with matrix A. What's up with matrix A? Symmetric from the hypotheses. So A transpose equals A. We get 2A minus A minus A, and we get the zero matrix out. So we've shown, remember what we're trying to show. We're trying to show B equals this quantity here. We've just shown B minus this quantity squared equals 0. Well, with matrices, that's not enough. I can have a matrix squared yield a zero matrix and yet not have the zero matrix necessarily over here. It depends on invertibility, ultimately, as we'll show on the next slide. But we're not done. I can't conclude from this that this quantity itself is a zero matrix. I can certainly have a matrix that when I square it, I get the zero matrix. And I didn't start with the zero matrix. Take a 2 by 2 matrix with the lower left-hand entry of a 1 and the other 3 entries 0. You square that matrix, you'll get the zero matrix. And yet it's not the zero matrix itself. So sometimes non-zero matrices squared equal the zero matrix. We ain't done. All right, matrix B was symmetric by hypothesis. There's that hypothesis right there. VC to the 1/2 V transpose is symmetric. Transpose it, you'll get this matrix back. Remember, C to the 1/2 is a diagonal matrix. Oh, there that is explicitly right there. So both of those are symmetric, so the difference is symmetric. So we've got, on the previous slide, we had this matrix squared equals a zero matrix. And this is a symmetric matrix. Well, if we take any old symmetric matrix S squared is S times S transpose, because S equals S transpose, because it's a symmetric matrix. And the ij entries of S squared are then the inner product of, think how you multiply matrices, it'd be the ith row of S with the jth column of S transpose. That's how you multiply matrices by definition. Oh, but the ith column of S transpose is the ith row of matrix S. And so we get, for the ij entries, for the ii entries, we're getting S sub I. We're getting the norm of that ith row squared. S sub I is represents this lowercase s sub I represents the ith column of matrix S. So what we're ultimately getting is a Frobenius norm for the columns. Well, the only way we could have S squared equals 0 is then for each of those columns to have norm 0. The only vectors, we're going to place now. The only vectors with a norm of 0, it's an L2 norm or Euclidean norm, if you like, for vectors, or the Frobenius norm for matrices, however you want to view it. But the only way that norm can be 0 is if all those components of that column are 0. And the only way for a symmetric matrix to square and give 0 is for us to have the 0 matrix. Since B minus this matrix is symmetric and it's squared to equal 0, then this must equal 0, or in other words, B must equal VC to the 1/2 B transpose. So punchline is, if we have B squared equals A, then we must have B of this form here. That's the uniqueness of square roots. Back to the notes. In this section, and shifting gears a little bit, now we're looking at the Cholesky factorizations. So here's a definition of a Cholesky factorization. Let A be a symmetric positive definite matrix. If A equals, sorry for all the T's, T transpose T, where capital T is an upper triangular matrix with positive diagonal entries. So really there's the hypotheses to require a matrix or a factorization of this sort to be a Cholesky factorization. Then A equals T transpose T is a Cholesky factorization of A. So you're taking matrix A, writing it, we call these Gramian products somewhere back in chapter 3, where we're using a matrix T in that Gramian product, where T is upper triangular with positive diagonal entries. Such a thing is a Cholesky factorization. All right, first result is, if we have a symmetric positive definite matrix, and that's the topic, in part at least, of this section, then A has a Cholesky factorization. So symmetric positive definite matrices have Cholesky factorizations, first result. Little comment, the next two theorems I've got from a different source. I've given you the reference here. We're okay with internet sources as long as the math stands up, and it does. Let's go through a proof. 5.2.9 says, symmetric positive definite matrix A has a Cholesky factorization. Okay, we'll do it by induction. So here comes a base case. If we have a 1-by-1 matrix, say A is little a sub 1, 1. Little a sub 1, 1 must be positive. We had a positive definite matrix. So easy from the definition to see A1, 1 must be positive. So we could take T to be the square root of A sub 1, 1, and then T transpose would be the same thing. When you multiply the matrices together, you get matrix A. So 1-by-1 matrices, 1-by-1 symmetric positive definite matrices have Cholesky factorizations. I guess the symmetry is what, vacuous for 1-by-1 matrices. The positive definiteness we need, or else we can't take that square root here. All right, now suppose all n-by-n symmetric positive definite matrices have a Cholesky factorization or Cholesky decomposition, and consider a matrix A that's n plus 1 by n plus 1. All right, we're going to partition so we can get to that induction hypothesis. Partition A into 4 pieces, make the upper left-hand partition be that's simply that single entry, the A sub 1, 1. If you like, we're taking capital A sub 1, 1 to be the 1-by-1 matrix with A1, 1 in it as its only entry. You might argue I should have square brackets around that. That wouldn't be unreasonable. But this is not a silly notation for a matrix partitioned in this sort. There is a Schur complement of A1, 1 in this matrix. Schur complements were defined to be Z equals A2, 2. Remember this? The Schur complement was this minus this times that inverse times the other. Matrix, matrix inverse times matrix. The inverse of this, well, it's simply the 1-by-1 matrix, 1 over A1, 1. Another thing, good thing A1, 1 was not 0. It's where the positive definite part's coming in. So this was the Schur complement. Remember that. We're going to go through and deal with the Schur complement a little bit. When we have a Schur complement of a symmetric positive definite matrix, the Schur complement itself is symmetric and positive definiteness, a claim left to an exercise. So Z itself is symmetric and positive definite, and it's n by n. So we've removed a row and column. When we look at a Schur complement, we're dealing with in this case, with an n by n matrix Z. So the induction hypothesis applies to matrix Z to say it has a Cholesky factorization. Let's call it T sub Z transpose times T sub Z, where T sub Z is as desired, upper triangular with positive diagonal entries. So there's the induction step. Define matrix T as T equals square root of A11. This would be what, a row vector of appropriate size, and that T sub Z that we just saw. Now, T sub Z was upper triangular. Okay, so that means zeros below the diagonal. This matrix, T itself, below the diagonal, there's all zeros. There's a column of zeros here after that first entry, and then below the diagonal of T sub Z, there's zeros. So yeah, below the diagonal, we've got all zeros. So indeed, T is itself upper triangular. It also has positive diagonal entries. T sub Z had positive diagonal entries. The only new thing here is this, and we said A11 was greater than 0, so that's positive as well. So T also has these two properties. That is, T itself is upper triangular with positive diagonal entries. And it's the right thing, it turns out. So we'll take T transpose times T, and we'll get matrix A out. Here's T from above, transpose it, which involves transposing the diagonal elements, some interchanging and transposing. So that's how you transpose a partition matrix. So we got a transpose picked up over here. This can be written as, let's see, doing the multiplication, we lose a square root here. Do your usual row times column stuff. I won't bore you with the details. We get this. I guess we get this first. Hey, we got a T sub Z transpose T sub Z, but remember that was a Cholesky factorization of Z. So I replace that with Z, and one other thing. Let's take that A12 transpose. Remember, A was symmetric by hypotheses. That means A12 transpose equals A21 in the partition representation of matrix A. Conveniently, here it is. So if I transpose this, I get that. If I transpose this, I get that, since A is a symmetric matrix. So let's replace the A12 transpose here with an A21. Can be done. And then we've got almost what we need, except in this entry down here, we're supposed to get matrix A back out. We get the A11, the A12, the A21. Oh, and remember, this is how you compute a Schur complement. Okay, so if I'll take this quantity to the other side, we'll have Z plus this, that's A22, justifies substituting A22 in for this stuff here. And indeed, you got matrix A back out. So A was an arbitrary n plus 1 by n plus 1 matrix. By induction, by induction on the dimensions of matrix A, any matrix A symmetric and positive definite has a Cholesky factorization. To the notes. Gentle gives an algorithm. It's a recursive algorithm to go through and find a matrix T that gives a Cholesky factorization for a symmetric positive definite matrix A. If we let the entries of T be T sub ij, then we get the following. There's nothing real productive in going through the details on this, other than to observe. We start out with the upper left-hand entry of the square root of A11. Should be a surprise after the proof we just saw. And then additional subscripted t values are defined in terms of previously defined t values. It really is a recursive definition, meaning, it could be quite time consuming to go through and find such a matrix T. But the claim is there's how you make matrix T to produce a Cholesky factorization in this particular setting. If A is an invertible matrix, we even get a bit of a converse of theorem 5.9.2. There was an if and only if relationship concerning the symmetry and the positive definiteness. An invertible matrix A, so extra hypotheses, has a Cholesky factorization if and only if. So there's, this includes the previous result and includes a new result. A is symmetric and positive definite. We just saw symmetric positive definite implies Cholesky factorization. We get the converse of that when considering invertible matrices. And I think this is probably our last proof. So let's look at that. Okay. If A is symmetric and positive definite, we just saw it has a Cholesky factorization. That was the previous result. The invertibility of A has nothing to do with that. All right, next, suppose A is invertible and has a Cholesky factorization. We want to show A is symmetric and positive definite. Having a Cholesky factorization means A equals T transpose T, where T has this certain properties. So if we transpose A, that is if we transpose T, with all these T's flying around, when the dust settles, we get T transpose T, we get matrix A back. A equals its transpose. A is symmetric. Okay, now we need to show the positive definite part. To do that, we'll take X, a non-zero vector in Rn, and consider the quadratic form. Remember what positive definite was? For any non-zero vector X, X transpose AX, this should be positive definite. This should be strictly positive, strictly greater than 0. Okay, so we'll do some substitution. We haven't used the properties of T in anything we've done yet. So we've got upper triangular and positive diagonal entries for T. Okay, so take A, replace it with the T transpose T, hypothesized Cholesky factorization. Let's take these first two, X transpose T transpose, rewrite that as XT transpose. Now we've got a vector transposed times itself. That's just an inner product. Hey, the inner product of a vector with itself, that produces the Euclidean norm or the Frobenius norm. You want to think of it as a matrix, 1 by something or something by 1. But that produces a norm. Okay, if it's a norm, then we've immediately got X transpose AX is greater than or equal to 0. So we've got non-negative definite at this stage. We want more than that. We want positive definite. So call this equation star, where we've related X transpose AX, related that quadratic form to this norm. Okay, we just need to wrap it up and make sure that we're dealing definitely with positive stuff and not 0. A was hypothesized to be invertible, a hypothesis we haven't used yet. So theorem 3.3.16 tells us that means the determinant of A is non-zero. You're used to this from linear algebra. Invertible, determinant's non-zero. Also, the determinant of A is the determinant of T transpose T. That's the Cholesky factorization of A. The determinant of a product is the product of the determinants. There's the theorem that justifies that. The determinant of a matrix and its transpose are the same. Theorem 3.1.a, I guess. So we've got simplifying determinant of A equals a determinant of T squared. Well, if the determinant of A is non-zero, and we have this relationship, then the determinant of T is non-zero. And so T is invertible. Theorem 3.3.16 as well. So if we take a non-zero X, we have to have T of X as non-zero. Maybe look at the contrapositive of that. If we had T of X equals 0, think of it as a system of equations, and T is invertible, which we do have, T is invertible, then we gotta have X equals 0. Contrapositive of that, if x is not 0, then t of x is not 0, where t is invertible. So when we look at that norm of t of x, we ain't looking at the norm of the 0 vector. Well, the only vector with a norm 0 is the 0 vector, so we're not getting a norm of 0. We had related x transpose ax to this norm. Well, that norm is not 0, it must be positive then, and so that quadratic form must be positive. In other words, A must be positive definite. We've shown A is symmetric and positive definite, assuming a Cholesky factorization, and that's what we were trying to show. A little bit more from this section. If we deal with a symmetric positive definite matrix, we've shown that such matrices do have Cholesky factorizations. In fact, they're unique. It's to be shown in one of the exercises, so there's a uniqueness result. We'll wrap up this section and pretty much the course. There's not much in the final section. With some observations about products of the form x transpose x, where x is a matrix. These we call Gramian, the Gramian matrix, one that's of that form, the Gramian product as well, I think. First, x transpose x, hey, it's symmetric. That's straightforward. Transpose it, you get the same thing back. So theorem 3.8.a says it's orthogonally diagonalizable. Let's check that out. So just a little laundry list of such properties. I think I have that. Here it is. From section 3.8, the eigenanalysis section, the lengthy eigenanalysis section, says orthogonally diagonalizable if and only if symmetric with real entries. And so this is just that observation. Orthogonally diagonalizable, it can be written in this form. V is orthogonal, yeah, so orthogonally diagonalizable. C is diagonal matrix, is part of the story as well. If matrix X, we're talking about two matrices, X and the Gramian matrix, X transpose X. If X has a QR factorization, remember that meant Q was orthogonal, R was upper triangular with positive diagonal entries, then we had some conditions under which that occurs, but then we can take X transpose X and write, let's see, X is Q times R, that's the factorization of X, Q times R transpose for X transpose. Do your deal with transposes, we get R transpose, Q transpose, Q. That's the identity because these are involve orthogonal matrices, so we've lost that. We get R transpose times R. What was up with R? Upper triangular with positive diagonal entries. Why? That's exactly what a Cholesky factorization is. So we just showed, this is really a little theorem, if X has a QR factorization, then X transpose X has a Cholesky factorization. In fact, it's given by R transpose R. Easy little computation on that one. Like I said, this last little part's just a bunch of little results about X transpose X. We saw back in theorem 3.8.16 that every matrix has a singular value decomposition. That is, every matrix can be written in the form U, D, V transpose. U and V are orthogonal. D is diagonal. D has the same dimensions as X. So this is that case where we were talking about a diagonal matrix. Maybe it ain't square. If matrix X isn't square, then matrix D is not square. But we still have a meaning for diagonal for non-square matrices. So if we take X transpose X, substitute this stuff in. U, D, V transpose transpose, U, D, V transpose. Do your transpose thing on that product of 3, giving us V transpose transpose, or just V, D transpose. D's diagonal, so that's just D as well. U transpose, okay, here's the rest of it. Hey, U transpose, that'll give us an identity. We can drop that. We get V, D transpose, D, V transpose. That can be written in a certain style. We get X transpose X then can be written, if you'll insert some transposes back here, you get dV transpose times dV transpose, which is just an amusing little relationship. We got some things to simplify that produced it as a product of this form. Back up here, hey, D transpose D, that's itself a diagonal matrix. So we've actually, from this relationship, we've got X transpose X written as V, D transpose D, V transpose, where that thing inside is a diagonal matrix. Remember, V is an orthogonal matrix. So we've written this Gramian matrix as V times diagonal matrix times V transpose, where the V is orthogonal. Then that's an orthogonal diagonalization of the Gramian matrix X transpose X. And a final observation, Theorem 3.8.7 part 4 implies that the real eigenvalues of X transpose X are the squares of the eigenvalues of X. Let's see if I can find that. It dealt with, oh, good shooting, hey, there it is right there. Dealt with part 4, a product of that sort, X transpose X. We get into this by saying C is an eigenvalue of matrix A, then X transpose X has C times C conjugate as an eigenvalue. Well, if C is real, as we just stated in that result, C conjugate equals C, and this is just C times C. So then we get C squared as an eigenvalue of that Gramian matrix. That last sentence is simply a restatement of that. They assume real eigenvalues, so you're getting squares of eigenvalues of the original matrix. And that takes care of Cholesky factorizations. We got one little section left, and it ain't a long one. So the end is near. I'll see you in section 5.10, is it? And we'll wrap this thing up. Have a nice day.